Welcome to the class, and what we are going to study today is basically look at this actual Mimo transmission. What we have seen today till now is that we are transmitting only a single symbol x, okay. Whether we want to transmit the actual data, okay, it's always limited to a single symbol transmission, wherein you have multiple transmit antennas, right? What are we essentially doing? Take x and precode it, but that x is basically a single x, okay. We are not transmitting information in parallel. I will explain that notion of parallel. Basically, what are we saying here? You can transmit x1 and x2 from two different antennas, okay, right? And how do we do that? That's what I am going to show you, okay. But where does this come into picture, and where it is it helps, that's what we are going to see, okay. So, but before that, this is a quick summary of this previous class. Sounding reference signals are required for estimating the uplink channel. Then for TDD system, downlink channel is same as uplink channel, okay, right. If time permits, I will show you how downlink channel is slightly different from uplink channel, even in case of TDD, okay. That's the actual, that's what happens in practice, okay. But for whatever you wanted to learn, okay, the notion of this channel reciprocity, this is essentially what it means, okay, that for TDD systems, downlink channel is same as uplink channel, okay. Now, sounding reference signals are required for estimating the uplink channel, okay. And then base station transmits CSI-RS for the UE to calculate the MCS and feed it back to the G node B, right, okay. Then this G node B transmits this DMRS along with data for UE to estimate the recorded channel, right, which is used for downlink for decoding the data, and this is basically the reference for whatever we have discussed, okay. Now, what we are going to focus on from now is this Mimo transmission, okay, and where it actually comes into picture, where it is applicable, okay, is basically at high SNR, okay, right. And what we showed in this case was that if the high SNR, if the system is operating at high SNR, the capacity increases logarithmically with SNR, okay. If you increase, it's basically log to the base 2 and then the SNR, right. If you increase SNR by a factor of 16, then the capacity increases only by a factor of 4. So, SNR is not very impressive if the system is already in high SNR regime, okay. Now, what I am going to show you is, okay, that in this case in high SNR, where increasing the SNR is basically not very tempting, okay, do something different to basically get a linear increase in the capacity, which happened at the low SNR case, right, okay. So, in low SNR case, if you increase the SNR, the capacity increases linearly with SNR, right. Can you do something like that at high SNR case in high SNR regime? Yes, you could, okay, and that is where this concept of multiple transmit and multiple receive antenna come into picture, okay, right. Till now, what we have considered is basically either multiple transmit antenna or multiple receive antennas, okay, right. What happens if there are multiple transmit and multiple receive antennas, okay? You immediately see, okay, what am I doing here? Instead of transmitting x and x from both these antennas, what are we doing? I am transmitting x1 from first antenna and x2 from second antenna, two different symbols, okay. And if you remember our PDSCH 5G framework, what it essentially means here is you are doing this exercise on the same resource element, okay, right. So, I am not transmitting x1 on first resource element and x2 on second resource element, I am not doing that, okay. What am I doing here? I am transmitting x1 and x2 on same resource element, okay, right. So, that is what is happening. Now, if that happens, okay, so because they are being transmitted from same resource element, they will interfere with each other, right, okay. And how will they interfere? We will see, okay, we will define the channel exactly and then we will see how they interfere, okay. So, what I am in this example, what am I considering? I am considering this 2 transmit antenna and 2 receive antenna, okay, right, just for the sake of simplicity. Now, what happens here is I will make you understand this notation also, because we are introducing it for the first time, okay. So, but primarily what are we saying here? What is the signal being transmitted? Okay, you see that in this case I am not even precoding the signal. Even though I have two transmit antennas, I am not even precoding the signal. Then also it will give you a lot of gain, okay, right? And we will see that, okay. So, is the framework clear? So, I am transmitting x1 by root 2 and x2 by root 2 from two different antennas, okay. So, if x1 has power p and x2 has power p, what is the total transmit power? Total transmit power will still be p. So, this power is p by 2 and this power is p by 2, correct, okay. So, now let us look at this case, this system basically, okay. So, I am focusing on this signal, this part of the system. What will happen, okay, right? Or let us say, so this is, okay, what am I saying here, okay. So, instead of this, what am I do something, I will focus on this part of the system, okay, right. Now, so what are we saying here? Two transmit and single receive antenna case, okay. This, it looks like that, right, okay. So, what is happening here? So, what are we doing? Transmit x1 from by root 2 from first antenna and x2 by root 2 from second antenna. Now, what am I saying here? That what is the signal being received at the first receive antenna, okay. Let us see this, okay. So, receive signal at first antenna, I call this as, let us read the notation carefully, okay. This is the signal being received at first receive antenna, okay, correct. And what is the signal being received at first receive antenna? Is the sum of these two signals after getting multiplied by two different channels, okay. So, you see this, what is this? This is a signal being transmitted x1 by root 2 and it is getting multiplied by what? H11. Now, what is this H11? Okay, is the channel from, you have to read this notation carefully, channel from first transmit antenna, okay. This subscript denotes the transmit antenna and this subscript denotes the receive antenna, okay, right. So, what is this? Channel from first transmit antenna to first receive antenna, right, okay. That is how we are denoting it, you see this. This is a channel from first transmit antenna to first receive antenna. And what is this channel? Channel from second transmit antenna to first receive antenna, right, okay, correct, okay. So, what will happen? Channel from, this is a signal from first transmit antenna getting multiplied by channel from H11, signal from second transmit antenna getting multiplied by channel from second transmit antenna to first receive antenna, okay, right. So, just to make sure that we have gotten it, what is H11? Channel from first transmit antenna to first receive antenna. What will be H12? Channel from second transmit antenna to first receive antenna, right. So, that is what is happening over here, correct, okay. So, this is the signal being received at first transmit antenna. Similarly, what will happen to the second receive antenna? Let us look at this. What is the notation? Channel from what? Let us what will happen? Where are we looking? We are looking at a second receive antenna. So, what is this? Channel from first transmit antenna to second receive antenna. Similarly, so this is this channel, right, first transmit antenna to second receive antenna. And what is this channel? From second transmit antenna to second receive antenna, right. And now, where are we looking? We are looking at this receive antenna, right. So, we have to look at these channels and what will be the signal received at this antenna? It will be x1 by root 2, this is the signal being transmitted from first antenna getting multiplied by this channel plus signal being transmitted from this antenna getting multiplied by signal from this, from channel from this antenna and plus noise, right, okay. So, just to summarize about the notation, this subscript denotes the transmit antenna and this subscript denotes the receive antenna, right. So, this is our system of equations. Is this clear? Okay. So, let us move ahead. So, this is our system of equations. Now, I will write it in a slightly more generic form so that it becomes easy for us to handle the system after this. So what am I doing here? I am writing it as vector y, vector h, matrix h, vector x plus noise. Okay, right? Now how am I defining this vectors and matrices? Let us see this. Okay, right? What am I calling? It becomes, if you look at this, I am calling this as vector y. I am calling this as vector n. I am calling what is, if you look at this, this is slightly twisted if you are looking at it for the first time. Okay, what is this? If I define vector x, it will come here. Okay, if I define vector x as something like this, what is this? If I put transpose over here, what am I calling it? x1 by root 2, x2 by root 2. I have defined the vector like this. Okay, right? And if I define a matrix H, okay, this is noise. Okay, if I define a channel like this, H11, H12, H21 and H22, correct? Okay, right? Then what is H of x? Let us write x as the like this, x by x1 by root 2 root 2. If you multiply this, won't you get this product? If I call this as h of x, that is what we are writing over here. What is this? What will y1 be? It will be h11 into x1 by root 2 plus h12 into x2 by root 2 plus noise n1, right? Okay, correct? This is the reason we define this channel in this particular notation. Okay, right? So that's the idea. It's like if you have seen it earlier, it's very easy to understand. Okay, but for the students who are looking at it for the first time, this is the notation for any generic channel H. Okay, right? So now this is the system of equation. Right? Okay. Now, what is the job of the UE? What were the two symbols which were transmitted? x1 and x2. And what is the system? What is the signal it has received? Y. Correct? Okay. Now, let us say UE knows this channel H. Okay. I will tell you how it is estimated, what kind of pilot signals need to be estimated, needs to be transmitted for the UE to estimate this channel H. That we will see later, but let us assume that UE has this channel information. Okay, right? So how will it detect x1 and x2? What will it do? Okay, right? So what am I done? It has this received signal y. Okay, what is it going to do? It's going to multiply it with H inverse. Okay, right? Okay, so let's look at this. Okay, what is the size of H? Is a 2 cross 2 matrix, correct? And what is the size of H inverse? It will again be a 2 cross 2 matrix. Okay, what is the size of y? Y is 2 cross 1, right? What is the size of y tilde? 2 cross 1, correct? Okay, so now if this operation is done, what will be the output? What is y? If you substitute y over here, what are you going to get? X plus H inverse n, right? Okay, now if the UE looks at the first component of y tilde, what is it going to get? If you look at this, we call this y1 tilde and y2 tilde, what is it going to get? x1, x2, right? Plus I call this as n tilde, just for example, plus what is it going to get? n1 tilde and n2 tilde, right? Okay. Now, so what is UE going to do? It's going to look at the first component of y1 tilde, it will get noisy version of x1. It's going to look at second component of y2 tilde, it's going to get noisy version of x2, right? So it has basically decoded x1 and x2 or detected x1 and x2. Okay. The key fact over here is, okay, these two receive signals, these two receive antennas, okay, are helping the user in basically detecting these two symbols, right? Okay, and transmitter is aware of this fact, okay, that UE has two receive antennas. Okay, if UE has only one receive antenna, this kind of two symbol transmission cannot happen. Okay, you can think about it why. Okay, I'll give you the answer also. Okay, now, but in this case, because UE has two receive antennas, base station is transmitting two transmit symbols in parallel. Okay, right? So let's say, just for example, okay, that if a UE is transmitted 1 PRB, okay, now without this it can transmit only 12 symbols if nothing is used for transmitting pilots. Okay, 12 REs, 12 symbols. But with this kind of transmission, base station can transmit 24 symbols over the same PRB for this user. So what has base station achieved? It has basically doubled the data rate, right? Okay, and double the data rate by using the fact that user has two receive antennas in this case. Okay, earlier also base station had two transmit antennas, but UE had only single receive antenna. Okay, it could not do this, so the data rate was not doubled. Okay, right? But where was that kind of system enticing? In low SNR regime, wherein those two transmit antennas were used to increase the SNR, right? Okay, you remember, if you precode the signal and then basically the SNR increases, right? Okay, and that is very effective and very effective at low SNR regime. But at high SNR regime, where increase in SNR is not giving us a lot of gain, you have to do this kind of transmission. Okay, and that's a Mimo transmission. And if you look at the standard, that's what also it does. Okay, it defines this kind of transmission in a particular way. Okay, we'll learn all that framework. Okay, but I've introduced you to this Mimo transmission, wherein it is basically base station is able to transmit two data symbols in parallel, right? Okay, and another key aspect, this kind of transmission is basically possible. Okay, this kind of gain is possible even though transmitter does not have the channel information. See this, we do not use the channel information, we do not have it. Okay, right? So still get the gain. Okay, but what happens if transmitter has the channel information? Even in this case of Mimo transmission, okay, you can show that you will perform better, much better than what we did just now. Okay, right? And I'm going to take you to that exercise also. We'll do that exercise, because that's also very crucial. Okay, right? But till now, so what we have assumed here is the transmitter does not have the channel information. Okay, right? And what am I saying here? Capacity will further be increased if transmitter has the channel information. Okay, right? And you will see this in this case basically. So what happens if you look at Y? Okay, right? You look at Y1 and look at Y2. These two, X1 and X2, are interfering with each other, right? Okay, because Y1 has both X1 and X2. Similarly, you look at Y2. Okay, Y2 contains X1 and X2, right? And this is called interstream interference. Okay, and you are transmitting two data streams in parallel. Okay, so this interference which you see here in Y1 is, and similarly in Y2, like it's called interstream interference. And who is cancelling that interference? Receiver. Because what is receiver is UE. What is UE doing? It's multiplying it with the H inverse. Okay, and if it does this operation, what happens? If you look at Y tilde, there is no interference in Y tilde, right? Because if you look at first component of Y tilde, you get X1. Look at second component of Y tilde, you get X2. Correct? Okay. So who has cancelled that information? That interference? Only the receiver. Okay. Now, if transmitter has the channel information, part of this interference is cancelled at the transmitter, and part of the this interference is cancelled at the receiver. We'll take an example. Okay, and I'll show you that this, when transmitter has the channel information, okay, the capacity increases further. Okay, and now we take a step towards that, and I'll just introduce you to something. This is called singular value decomposition. Okay, we'll use this framework to basically precode the signal for Mimo transmission at the transmitter. Okay, right? I'm going to show you. We'll do that exercise in the next class, but I'll start introducing you to this very nice decomposition. Okay, it's called the singular value decomposition. Okay, even if you have not heard about it earlier, it doesn't matter. Okay, whatever is required for us to understand this, like precoded Mimo transmission, okay, which is going to increase the capacity further. Basically, this is the idea which is covered in this slide. Okay, we'll see that. What are we saying here? That any NR cross NT matrix, right? matrix can be of any dimension, rectangular, square. Okay. What are we saying here? Any NR cross NT matrix can be decomposed using SVD as follows. Okay. So, if H is a matrix, what is the dimension of H? It is NR cross NT. NR number of rows and NT number of columns. Okay. Right? It can be decomposed as this: W lambda V Hermitian. What is W? Okay. What are we saying here? So, what is the size of W? It is NR cross NL. I will define NL also. Okay. And what is the size of V Hermitian? It is NL cross NT. Okay. Right. And now, if W and V have these sizes, what will be the size of lambda? Lambda is this matrix sitting in between. It will be of size NL cross NL, right? Okay, because dimension should match. Okay, if you are doing this matrix product, the dimension should match. Okay, right? So, lambda is a diagonal matrix. Okay, so this is what is the key feature of W and V. Okay, W and V also have orthogonal columns and rows. Okay, W has orthogonal columns and V has orthogonal rows. Okay, V Hermitian has orthogonal rows. That is what we are saying here. Okay, and what is this lambda? Lambda is a diagonal matrix containing ordered singular values of H. Okay, so what are these? It is a diagonal matrix containing some positive numbers. Okay, and those positive numbers are called the singular values. That is why it is called the singular value decomposition. Okay, right. So, and how are they arranged in this decomposition? First number, first singular value is the largest singular value, second one is the second largest, and the last one is the smallest singular value. So, they are arranged in a decreasing order. Okay, right. And how many such singular values are there? NL. Right, that is what we saw. What is the size of lambda? Size of lambda is NL cross NL. Right, okay, correct. And what is this NL equal to? Okay, NL is equal to minimum of NR comma NT. Okay, and this is also called the rank of channel H. Okay, right. Now you go back and look at the earlier example we took. Okay, what were these numbers over there? It was H was a 2 cross 2 matrix, correct? Okay. So, what will be the size of W? It will be 2 cross NL, let us say, right? Okay. What is, so let us compute, okay, right? So, what is NR? NR is 2 and NT is 2, right? Okay. So, what will be the size of lambda? It has to be 2 cross 2, right? Okay. It can be 2 cross 1 also, but we will not look at that case, okay, right, for the time being. Now, so what are we saying here? Okay. What is this? NL is, what is NR? What is NT? NR is 2, NT is 2, and NL will become 2, right? That is how we are defining it in this slide. Okay. So, what are we saying? This is the previous example we took. What was the rank of channel H? 2, right? And what is it telling us? That this rank, okay, is basically will tell us how many such parallel symbols we can transmit, okay, right? And how many parallel symbols did we transmit in the last case? 2, right? If let us say NR is 4 and NT is 4, right? How many parallel symbols can we transmit? 4, because the rank has, channel rank is 4. Now, go back and see, think about that case wherein NT was 2 and NR was 1. What will be the rank of the channel matrix? Because it is minimum of NR comma NT, right? Okay, NL, right, the rank of the channel is 1, correct? So, channel will not allow you to transmit more than one symbol, okay. In this case, just to understand, okay, H was 2 cross 2, it allowed us to transmit 2 symbols in parallel. If it is 4 cross 4, it will allow us to transmit 4 symbols in parallel. If it is a 4 cross 2 system, again, what will the rank of the channel? 2, right? Even though you have 4 transmit antenna and 2 receive antenna, you can only transmit 2 symbols in parallel, right? Another example, okay, right? If NT is 4 or if NT is 2 and NR is 4, again, what is NL? 2, right? So, what is it telling? That in order for this multi-stream transmission, okay, right, if you want to transmit the maximum number of streams, which is equal to, let us say, number of transmit antennas, okay, right, then number of transmit antennas should be same as number of receive antennas, okay, right, otherwise the system gets limited by the minimum number of antennas, okay, right, and this is the idea which is used in 5G, okay. So NL, the standard uses a specific term, it is called as layers, okay. NL, that is why I wrote as NL, okay, the number of layers, okay, which is equal to the channel rank, okay, right. So for our systems, whatever we have considered, okay, for the multiple antenna multiple transmit antenna, single receive antenna, number of layer was 1, correct, okay. For a 2x2 system, number of layer was 2, right, and what happened there was, what is this multiple layer transmission? What does that mean? You are basically on the same PRB, you are transmitting double the number of symbols. If it is a 4x4 system, you will transmit 4 layers on the same PRB, 4 times the number of symbols on each PRB, right. You see this, where is this important? It is important in the case when your system is operating at a high SNR regime, right, okay, and as we discussed earlier, that in this high SNR regime, increasing SNR is giving you diminishing returns, okay, because you are not able to increase the capacity. Now you see this, okay, with every doubling of antenna, my capacity is getting doubled, right, from 1 to 2 antennas, I am transmitting double the number of symbols, which is essentially doubling the data rate, right, or doubling the capacity, right. Similarly, you make it NT cross NT, 64 cross 64, your signal becomes, your data rate becomes 64 times, right, okay. Now the thing here is, you typically do not have 64 receive antennas if it is a downlink system, because if you are looking at the downlink, your mobile can have maximum 1 or 2 antennas, right, okay, correct. So how do you realize this number of layers, okay, how do you increase the number of layers? We will see that also. There is something called multi-user Mimo. I will not discuss that, I will let you think about it, okay, that because each UE can have maximum 1 or 2 antennas, but if you have 64 antennas, practically you can transmit 64 streams in parallel, right. You do not do that, let us say you transmit 8 streams in parallel, but for 8 streams, every mobile should have 8 antennas, and typically your mobile does not have. How do you use these kind of gains? That is where multi-user Mimo comes into picture. We will study that also, but we will stop here for today, okay. And what we have introduced here in this lecture is basically that if you have multiple transmit and multiple receive antennas, you can transmit multiple layers in parallel, okay. And this is the terminology we are going to use from now, layers, okay. And what is a layer? Layer is equal to the channel rank, that is all, okay. We stop here, thank you.